Great. Okay. Okay, thank you so much for coming, everyone. Today we have Ethan Partida from Brown talking about graded Ehrhart theory of unimodular zonotopes. Before we begin, let's go over our community statement. So we are all learning, everyone has something to contribute, and no one has all the answers. So with that, I'll pass it off to Ethan.
Great. Thanks for the introduction. Thanks everybody for showing up virtually. Today I was going to talk about a project of mine, joint with Colin Crowley, who's at Oregon right now, on graded Ehrhart theory of unimodular zonotopes. And I'll try my best to keep track of like chat and hands raised, but please like interrupt me audioly if you can, because then I will definitely respond to a question. I'm happy to respond to questions. Okay, so I wanted to start with sort of an overview of what's going on with this project. Oh, no. My screen is frozen. I'm not sure if I'm here still.
I can see I can see the next slide that you slided to.
Okay, did
I
I
can,
cut out?
you cut out for a
You
second,
cut
but
out
you're
for a second, yeah.
Okay, so hopefully that doesn't continue. Here's the slide. Okay, so the slide is as follows. So I'm trying to introduce Ehrhart theory here. And Ehrhart theory is this big, vast field, quite deep at this point, but it starts with a very simple question, which goes as follows. So you should fix a lattice polytope P, which will be a finite set of points inside of a vector space, Rn. And these finite set of points should have integer coordinates, and then you should take their convex hull. So here's an example of a polytope down in the corner. And you can ask this question, which you can, is how many lattice points are in this polytope? You can count them. And then you can sort of dilate and scale the polytope as you go along and try to count how many lattice points are in those respective dilates. So here is like a second dilate of that polytope. And if you go and sit down with the coordinates I've drawn, it is 19. And you can kind of keep asking these numbers, and you can respectively ask for the number of interior lattice points. So one's avoiding this boundary. And, it turns out that this question has lots of very beautiful answers, and the answers connect both combinatorics and commutative algebra and algebraic geometry, and they all say things about each other. And special to this project, if you specialize to a very special class of polytopes known as unimodular zonotopes, there'll be matroids floating around, and you can answer these sorts of questions using matroid theory. So things can be written in terms of an associated matroid, and maybe the matroids actually like inform some of the answers as well. So there's an older paper of Stanley which computes these numbers in terms of Tutte polynomials, and then Becchio, Hemko, and McCullough, they do many things, but in some of sense they study the Ehrhart series, which I will review. Okay. But the talk was on the graded Ehrhart theory of unimodular zonotopes. So what is graded Ehrhart theory? Graded Ehrhart theory is a recent q-analogue generalization of Ehrhart theory due to Reiner and Rhoades. And it goes as follows. So you're still fixing some lattice polytope P and a number M. And now for that dilated polytope, you're going to construct a polynomial, I sub P, which has non-negative integer coefficients, such that when I set Q back to 1, I'm recovering the number of lattice points in that mth dilate. So you can think about this as sort of a refined count of the lattice points. And now that you have these polynomials, you can ask the same question that was so fruitful for ordinary Ehrhart theory. So you should ask, how do these polynomials behave as I grow m? Now I'm asking a question about a polynomial instead of an actual number. And what I'm going to try to tell you about in the next hour or so is our answers to this question in the case of unimodular zonotopes. And I'm biased, but I think our answers, have lots of beautiful combinatorics, algebra, and connections to algebraic geometry when we try to answer these questions. And one of my favorite parts is that we really do use matroids to get to these answers. Okay. So this is where we're going. But I will spend some time kind of reviewing some facts from Ehrhart theory, things I like, and introducing graded Ehrhart theory in more detail now. Okay. So I have this slide. I like to think about it as like, in my biased perspective, like some trinity of Ehrhart theory. So there's a bunch of perspectives. There's sort of an enumerative side of things where you're really studying, maybe the generating function of the lattice point count. And it turns out that there's some polynomial called the Ehrhart polynomial that is very important in this world. And that's really living over here. And you can give an algebraic interpretation of all these objects in terms of some graded ring whose Hilbert series will encapsulate the Ehrhart series. This graded ring is known as the affine semigroup algebra. And if you're so inclined, you can interpret this graded ring as a coordinate ring of a projective toric variety, of which I've drawn a doodle of here. And you have all three of these perspectives have something to say about one another. Okay, so I wanted to start on that enumerative, like top left corner. And maybe the first theorem, and one of the best theorems in Ehrhart theory, is that there's actually a polynomial which gives you this answer to the question of how many lattice points are in the mth dilate. So if you fix some lattice polytope P, there will be a polynomial, which I'll denote by Ehr of P, known as the Ehrhart polynomial. And this polynomial has degree equal to the dimension of the polytope I started with, such that when I plug in some non-negative integer m to my polynomial, I get out the lattice point count of that dilate. And this should not at all be obvious from just the starting definitions. These numbers can change sort of quite rapidly, but it is a theorem of Ehrhart that this is true. And this polynomial obeys a wacky reciprocity law known as Ehrhart-McDonald reciprocity, which says if I plug in some negative number into the Ehrhart polynomial, which a priori should make no sense, it's just a polynomial and I know what it does on non-negative integers, but shouldn't mean anything for negative integers. Well, it actually does count something, and it counts the number of interior lattice points of that mth dilate. And so I drew an example down here. Will be our running example. And this is its Ehrhart polynomial. Notice it's t degree 2. And I also have some lattice point counts down here. And so you should notice that maybe if I plug in -2 to this Ehrhart polynomial, I will get out 7, which was the number of interior lattice points of that second dilate. Okay. And another thing you can do is you can construct a generating function that knows all of these graded lattice point counts at once. So what you do is you construct this Ehrhart series, which is the generating function such that the coefficient on t to the m is this number of lattice points in the mth dilate. And the Ehrhart polynomial, sort of by definition, is something called an integer-valued polynomial, which just means that when I plug in an integer to this polynomial, I get out an integer, which is true because this polynomial counts stuff. There's a general theory of the generating functions of integer-valued polynomials, which you could find in Stanley's EC1 or something. And this general theory implies that the generating function of this Ehrhart series can be written as a rational function. And it can be written as a rational function with a particularly nice form. So you have this denominator with a bunch of factors of 1 minus t, and then some numerator, which will be a polynomial with integer coefficients, which people call the H star polynomial, t. And then there's another beautiful theorem, this time due to Stanley, that this numerator is actually a polynomial with non-negative integer coefficients, which isn't true for just some arbitrary integer valued polynomials generating function. And so here's an example. Turns out when you do this expansion of this Ehrhart series of this polytope, you get this rational function. And now I have some numerator that has like non-negative coefficients, and I can hope it counts stuff. And maybe as a combinatorialist, I want like some interpretation of these coefficients. But Stanley's theorem, at least the proof I know and the proof Stanley originally gave, really does need algebra to go through. And I want to tell you at least a little bit about that. Okay, so we're going to construct this gadget, which will be known as the affine semigroup algebra. And this algebra will encode the various lattice point counts of these dilates. And the construction goes as follows. First, I want to construct this cone like convex shape inside of RD to the d plus 1. And you construct it by taking your polytope and putting it inside of a vector space of one higher dimension, and then taking and that polytope should be at height 1. So I've done that here. I took our hexagon and I placed it kind of at height 1 and R3. And then you should take the cone over that polytope. So take all rays emanating from the origin, which pass through that height, a polytope at height 1. And this will be some convex body. And then I want to let S of P be all of the lattice points in this convex body. And because this body is like a cone, it turns out these lattice points form a semigroup. So if I take any two lattice points and I add them together, like vector addition, I will get another lattice point inside of this cone. For example, I could take like this lattice point, and they're both at height 1. So their sum will be at height 2, and it'll also still have integer coordinates, and it'll be somewhere in the interior, maybe this one. And so the set of lattice points form a semigroup under a vector addition. And then there's a standard procedure to turn such a semigroup into an algebra. And so I've written the semigroup algebra here. And in this example, it turns out that the semigroup algebra is generated by the lattice points in this first dilate. So I'm using W here as a coordinate for the height. And essentially, so you can grade this algebra by this W coordinate, so the height. And by construction, the mth graded piece of this algebra will be the number of lattice points of degree and the mth dilate of P. And so you can construct this gadget called the Hilbert series, which is just the generating function that records the dimensions of the graded pieces. And this will be the Ehrhart series of your polytope P. Okay. And it turns out this algebra is very nice from an algebraic perspective. So it's a theorem of Hoxer that this algebra is something called Cohen-Macaulay, which is a niceness property. And since it's Cohen-Macaulay, you can talk about a canonical module, so this dualizing module. And it's a result of Stanley and separately Danilov in the context of toric varieties, that the canonical module of this algebra is isomorphic to a very special ideal. So it's the ideal generated by the interior lattice points. And I'm going to sort of black box both the canonical module and this Cohen-Macaulayness property, but I at least want to tell you what this ideal look like. So it has a geometric way of thinking about it. And what you do is you take this cone that you drew, the C sub P, and you place a copy of it at every single interior lattice point. And then you look at all the union of these lattice points inside of these unions of cones, and you look at the ideal generated by those. And so in this case, I would be placing this orange cone thing at every single one of these points. But it just so happens that all of the cones I placed at height 2 were already contained in this cone at height 1. And so as an ideal, this cone-shaped thing will only have like one emanating vertex, which is the generator of that ideal. And so this ideal is just the principal ideal generated by wxy, so this interior last point here. And Stanley worked through the commutative algebra, and he showed that these two theorems actually imply all of the enumerative ones from before. So it implies Stanley's theorem about the non-negativity of the numerator's coefficients in the Ehrhart series. It also implies this polynomial growth of the Ehrhart polynomial and the reciprocity statement as well. Maybe these are like things I really like about Ehrhart theory and are things we could hope are true in graded Ehrhart theory, which I wanted to touch on now. Okay, so this is a summary slide, and we still have maybe a trinity going on. And now the contexts are a little different. There will be a notion of a graded Ehrhart series, which will now be a generating function in two variables, t and q. And I'll say more about it, but there is like a noticeable lack of a graded Ehrhart polynomial, whatever that should be. For this, at least in the general case, there doesn't seem to be a graded Ehrhart polynomial. But Reiner and Rhoades, one of their theorems is that you do have an algebraic analog of this affine semigroup algebra, which will be a bigraded object. And this bigraded object will remember this two-variable Ehrhart series. And it's a result of E and KV, a recent result of E and KV, that there is a geometric interpretation of this object as a certain section ring on a blow-up of the toric variety, the polytope, which I've drawn as an explosion. Not accurate, but maybe evocative. Okay. But the construction takes a little bit of background to get through, mainly because it uses this machinery of orbit harmonics. And so I wanted to say a little bit about orbit harmonics. And so I'll start with the definition, and then the next slide I'll try to give some context. So what orbit harmonics is it's a machine that if you're handed some finite set of points inside of a vector space, orbit harmonics spits out a graded ring, denoting orb of x, whose total dimension is equal to the number of points you started with. But now this will be a graded ring, and so you can ask about the dimensions of the various graded pieces. And the sum of these various graded pieces dimensions will equal the number of points, but you're kind of given now a refined count of those points. Okay, and so the construction is as follows. Orb of x will be a quotient of a polynomial ring by this ideal Gur of x. And Gur of x is the ideal generated by the top degree homogeneous components of polynomials vanishing on your point set. And this is best illustrated, I think, through an example. So I'm going to take x to be this finite set of points, which happen to be the lattice points of my polytope. We should keep this in mind for later. And well, what I'm going to do is I'm going to try to find some polynomials that vanish on these 7 points. So the x coordinates of these points are either 0, 1, or 2. And so this polynomial in orange here will vanish on this, because it cuts out these 3 vertical lines. But I only want the top degree piece of it. And so when I do the binomial expansion of this polynomial, I should just take x every time. And so I'm going to get an x cubed term, a square I of x. And the same will hold true for these 3 green horizontal lines. And I'll get a y cubed. And then the last one to check is these blue diagonal lines. Cut out these points. And if you write down equations for them, they look like this. So some affine translates of the equation x minus y. And now I still only want the top degree piece. So every time I do the binomial expansion of these things, I should take x minus y times x minus y times x minus y. And I'll get an x minus y cubed. So these are 3 such things in this Gur I of x. And you have to check this, but it's true that these 3 terms actually generate the ideal Gur I of x. Okay. And then I'll have this ring, which is a quotient. And so I could find some monomial basis of it. And here, or not a monomial basis of it, but just a basis. And here is like one such basis of this quotient ring. And you can check for yourself that this basis has size 7, which is the number of lattice points I started with. But now the basis elements are all homogeneous of some degree, and so you could count them by their degree as well. So like we have two things of degree 1, it's basis. Okay. And so if this isn't helpful for you, you don't have to worry about it. But for me, it's quite helpful to think about. There's a geometric way to construct this ring, orb of x, as the coordinate ring of a scheme limit. So you should take your finite set of points and you should scale them towards the origin. So just scale them by some number epsilon. And then once epsilon is equal to 0, I'll just be left with the point 0. But if I do this in a schemy way, I'll be left with the point 0, but it'll be some thick point that remembered that it was 7 points coming towards the origin. And it'll remember something about the various directions in which these points came to the origin. Okay, so I keep this picture in mind when I'm thinking about this stuff. And I think orbit harmonics, it feels a little random when you see its definition, but I guess the thing that's convinced me that these rings are interesting is that they just appear in lots of contexts, and they've proven to be interesting in those contexts. So there's many examples where you have quotient rings you're interested in, and they turn out to be orbit harmonics rings. And this perspective is useful if you're trying to study these rings. And here's some list of things in which I know that they've appeared. I think there's more. Okay. But how will we use orbit harmonics? Well, I was talking about how we get this graded count of the points that we started with. And so we should just do that for our lattice points. So I'm going to define this I of P, this graded lattice point count, to be the Hilbert series of the orbit harmonics ring of the nth dilate lattice points. And similarly, this I tilde of should be the interior lattice points. And so I wrote out an example down here. I think the one to pay attention to is this first one here. So this should be the graded lattice point count of the first dilate. So it should be some polynomial in Q whose coefficients add up to 7. And how do we get these coefficients? Well, we should find a basis for the orbit harmonics ring and then count them by their degree, which I did here. So you can check that there's one thing of degree 0, 2 of degree 1, 3 of degree 2, and a single thing of degree 3. And to get these rest of them, I just kept doing that. Okay. And so with this definition in mind, we could define a graded Ehrhart series, which will just be a generating function now in 2 variables, which the coefficient on t to the m will keep track of the graded lattice point count of the mth dilate, completely analogous to the ordinary Ehrhart series. And same thing for this interior Ehrhart series. But as I remarked earlier, there doesn't, in general, seem to be like a notion of like a polynomial that's kind of counting coefficients here. But despite this fact, Reiner and Rhoades, they conjecture that a properties that you would expect polynomials general function. Namely, these graded series be written functions that particularly nice form. There's like 1 minus some t's and q's, and these t's and q's are allowed to have arbitrary non-negative powers. And then you'll have some numerator with integer coefficients, possibly negative. It's fine, because there are examples where they are negative, so you have to allow that. And that these generating functions obey some sort of reciprocity type statement as well. And analogous reciprocity statement for the ordinary Ehrhart series will follow from the reciprocity for the Ehrhart polynomial that I told you in the beginning. So these are like 2 conjectures on the Ehrhart series in a numerative sense, which are conjectured to hold for any lattice polytope. Okay. And so well, what's going on? So the in an analog to the affine semigroup algebra, Reiner and Rhoades, they defined these two algebraic gadgets, which will be bigraded algebraic gadgets, such that the bigraded Hilbert series, so the thing that keeps track of the dimension of the T-qth piece, is the Ehrhart series and is the Ehrhart series of the interior graded lattice point count. And they call these things the harmonic algebra, and I denote by H of P, and the interior ideal, which I denote by H tilde of P. And they conjecture that this algebra is a finitely generated Cohen-Macaulay algebra, and after a degree shift, this interior ideal is isomorphic to the canonical module. So this was the sort of theorem statement that was so nice in for ordinary Ehrhart theory, which Stanley used. Great effect. And this would be a great conjecture, but it turns out to be false in general. And it's the finite generation fails. An example due to KV. And I'll try to tell you at least a little bit about that example and the construction of these gadgets now. Okay, so what are we going to do? So we're going to build the harmonic algebra out of the data of the affine semigroup algebra using something called an associated graded ring. But to do that, I need this data of a filtration on my semigroup algebra. And you can think about this filtration as a sequence of subspaces of this ring thought of as a vector space. And I want these subspaces to contain each other as I go down. And I'll define you the filtration now as follows. This f of I will be the subspace spanned by polynomials, which vanish to degree at least I at the point 1, 1, 1, 1, 1. And this sometimes takes a little while to wrap your head around, but it's not so bad in an example. So I write out this semigroup algebra that we had before. And maybe a good one to pay attention to is this middle example I have here. So I claim that Wx minus W, which is definitely in the semigroup algebra, is in the subspace f of 1, but it's not an f of 2. And how do we check it's an f of 1? Well, we should check that once I set x equal to 1 and y equal to 1, this polynomial vanishes. And it does because 1 minus 1 is 0. So when I plug in x equals 1, this thing is 0. But it doesn't vanish to degree 2. And I can check that by taking a derivative in the x direction. So if I take d dx of this polynomial, I'm just left with the constant 1. 1 is not 0 when I plug in x equals 0, or x equals 1 and y equals 1. And so this thing doesn't vanish to degree 2, prevents it from being in this filtration, or this piece. And you can kind of keep going, which is what I did here, by taking various partials. And so this is the filtration. And once you're given this filtration, you can construct this gadget called the associated graded ring, which is a thing that does have a ring structure, but as a module, you can think about it as a vector space. You can think about it as these various vector space quotients of the ith filtered piece quotient out by the ith plus 1 filtered piece. And it's a result of KV that the harmonic algebra, so this isn't how Rhoades and Reiner define it, but it is isomorphic to this associated graded ring of the affine semigroup algebra. And a related object of this filtration, known as the Riesz algebra, appeared in the literature before, but in the context of Mori dream spaces in algebraic geometry. The people were like curious if such rings were finitely generated. And Gonzalez and Caru, they prove that if you take this funky looking triangle, which has coordinates here, in the plane, and you do this procedure, you get a non-finitely generated ring. Which I think is a very strange fact. The proof is like not so straightforward. There's like lots of things to check, which makes sense because I mean, like I don't really have like that many tools to like prove a ring is not finitely generated. Okay. And so this example, this example kills the finite generation of the harmonic algebra. But it doesn't necessarily kill these enumerative conjectures. So this is kind of a summary of what the state of the art of the general picture of graded Ehrhart theory is. So we still have these algebraic gadgets, but they won't be finitely generated in general. And there's a geometric interpretation, but don't exactly know what to use that for. And we still have these open conjectures on the enumeratives. Okay. And so now I want to tell you about my work where I'm studying these sorts of questions for unimodular zonotopes, which are quite structured polytopes. Okay. So I should start with telling you what a unimodular zonotope is, which I will do now. Okay. So a zonotope, a unimodular zonotope is a special kind of polytope that denote by the letter Z. And it's a polytope that you can get by taking some unit cube in a high dimensional vector space and then projecting it down into a lower dimensional vector space via a matrix. And this matrix should be tonally unimodular in the sense that all of its maximal minors should be 0, +1, or -1. So here's an example. I can take this matrix A here, which will give me a map from R3 to R2. And I can take the unit 3 cube. And what I'm going to do is I'm going to flatten it out. So in the Z direction becomes the X plus Y direction. And so you can imagine like flattening this 3 cube down and we'll be left with this hexagon we've been staring at the past 30 minutes. And so this gives witness to the fact that this hexagon is a unimodular sonotope. And you can get a surprisingly large number of interesting polytopes in this manner. It seems sort of limited at first. For example, the permutahedron, which is a favorite example of folks, is a unimodular sonotope. And this matrix here has an associated matroid formed by the columns of this matrix. And a matroid is this combinatorial gadget which encapsulates the dependency and independency of columns of matrices. And it's more general than that. So there's matroids that don't come from matrices. But in this talk, I'll always have a matrix floating around, so I won't worry about that. And so I'll give you one definition of a matroid, just so we have it. I'm going to say the matroid of this matrix A is its collection of independent sets. So this would be a collection of subsets of the column set. And the subset of the column set will be the columns that are independent. So you can do an example here. So if you look at this matrix and you pick any 2 columns, they'll be independent. They span R2. And so we'll be in our independent set collection. And any one vector is also independent, the empty set vector. The empty vector. The set of no vectors is independent. But if I took all 3 vectors, now I have 3 vectors in R2. And these have to be dependent. I have 3 vectors in a plane. And so that's to say that every subset of the column set is independent except for the set 1, 2, 3. And this will be my data of my matroid. And in this case, we say that the matroid is the rank 2 matroid. Okay. And associated to every matroid, there's like this fundamental invariant known as the Tutte polynomial. It's a bivariate polynomial, and it encapsulates like so much data of your matroid. It's like, such a beautiful polynomial invariant. But I won't define it for you. If you haven't seen it before, you can just think about a polynomial in 2 variables, and I can construct this polynomial given the data of a matroid. Okay. And so a result of Stanley tells us that this matroid associated to the matrix A actually knows like basically all the Ehrhart theory of the zonotope associated to it. So he's saying that if I take the nth dilate of a zonotope, well, it's the number of lattice points in that dilate is given by an evaluation of the tope. Same thing for this interior lattice. And this is a very nice formula. I mean, this Tutte polynomial is like the nicest polynomial you have a matroid in. So you're just evaluating. And some special facts about this evaluation is if I want to know the number of lattice points in just the first dilate, well, that'll be setting m equals to 1. And so I should know a Tutte of 2, 1. And this is the number of independent sets. Okay? So you can check in our old example that we had 7 independent sets, but there were 7 vertices of that hexagon, or lattice points of the hexagon. And if you want to know the interior lattice points, this is Tutte of 0, 1. And it's some sort of like alternating sum of the number of independent sets of size I. So this is what, I sub 2 is the number of independent sets of size 2. So it's like an Euler characteristic of the independence complex. Okay. And I just wanted to remark that Stanley's proof uses the valuativity property for splitting up a polytope and checking how many lattice points it has. And it's like not a canonical bijection between the set I, which has size equal to the number of lattice points for zonotope C. And in fact, there can't be a canonical bijection. The sort of symmetries are just wrong in some examples. And Bachman, Baker, and Liu, they do give bijections, but each of these bijections depends on a choice. But I think it's a little strange that, these two combinatorially defined sets are the same size, but they're honestly different. And I wanted to point that. Okay, so this slide is like, what is nice about zonotopes and their ordinary Ehrhart theory? And I want to tell you about the graded Ehrhart theory of these. Okay, so this is another summary slide. And the point is that there's lots of green check marks. So we prove all of Rhoades and Reiner's conjectures in this case. So that in particular, these harmonic algebras will be finitely generated, unlike the general case, and they're also, nice. And the enumerative conjectures are also true in this case. And I think like the two key ideas that we have are that, again, for the special case of unimodular zonotopes, there is a polynomial, which we call the graded Ehrhart polynomial, which plays the role of the ordinary Ehrhart polynomial. And you can do analogous statements. So this will be called like a quantum integer valued polynomial. And you can do like analogous type arguments as in the ordinary Ehrhart theory case using this graded Ehrhart polynomial to get all of these enumerative conjectures. And then on the algebraic side, we give an alternative description of this harmonic algebra in terms of a coordinate ring of a very special variety called the arrangement Schubert variety. So our algebro-geometric interpretation is what lets us prove all of these facts. These are very well studied and nice varieties. I want to tell you a little bit about that, but I'll start in the enumerative aspect. And actually, I'm going to start with kind of this fundamental observation that started the whole project with Colin. And it's that the orbit harmonics rings of the lattice points of unimodular zonotopes are very well controlled. And so they'll always be quotients of powers of linear forms in the sense that we have here. So, x minus y is some linear form, and I'm taking a power of it. And these have appeared before and are well studied. They're objects known as zonotopal algebras. And these have been studied by many authors. But maybe two of the first papers are by Holtz and Rod and Ardila-Postnikov. And the idea for why this is true, I think, is nicely illustrated through our example. Basically, every zonotope will have these sets of parallel faces. And these parallel faces are cut out by some linear equations. Right, so like this green one here was cut out by, x. And then what I want to do is I want to take this equation and I want to take a bunch of linear affine translates of it, which was what we were doing here. And same thing with the blue and the orange. So all these sets of parallel faces. And because I'm just taking affine translates, once I take the top degree piece, I'll forget about all those translates and I'll be left with some powers of these equations cutting out the parallel faces. And this is kind of true in general. I hope the picture was at least somewhat evocative. I'm going to black box the connection to zonotope algebras from here on out. Okay, so the first theorem, essentially because zonotopal algebras are so well studied, Colin and I were able to piece together what happens as you're dilating the polytope and get a formula for the graded lattice point count of the mth dilate of a zonotope, unimodular zonotope. And to tell you this formula, I need the q integers. So we can let m sub q be this polynomial of powers of q. And the important thing to note about this polynomial is that when I plug in q equals 1, I recover m, the number m. And so we give this expression. And I think the main thing to note about this expression is that up to this degree shift in the first part and in the second component, our expression for these lattice point counts are essentially take Stanley's and replace everywhere you see an integer with like a q integer. Okay. So I think this is quite nice. And one reason I think it's quite nice is, I actually have an example. So that's much better than telling you why I think it's nice. Here's an example. So I wrote out the example for our usual zonotope we've been working with. And remember, this was the graded lattice point count of the first dilate, this polynomial here. And you'll have to believe me, but the top polynomial of U23 is given by this thing. And what our theorem says is that you should multiply by q on the outside, and then plug in 1 plus q and q inverse to this top polynomial. And you'll get out this thing. And you can check for yourself that this is going to be true. Okay. Now with an example done, I can say why I like this theorem. And it's essentially because the top polynomial is a polynomial. So and this lets us put our work in the context of quantum integer valued polynomials, which are an object introduced by Nate Harriman and Sam Hopkins. And the definition's not so bad, so I'll give it. So we say a polynomial whose coefficients are rational functions in Q is quantum integer valued if whenever I plug in a Q integer, I get an honest Laurent polynomial whose coefficients are in Z. And the one thing to note about this definition is, once I set Q equals to 1, I recover the definition of an integer valued polynomial, in the sense that if I plug in any integer m, I'll actually get an integer. Okay. And working with this Tutte polynomial evaluation that we gave in the previous slide, doing some arithmetic, Colin and I were able to construct a quantum integer valued polynomial, which we call the graded Ehrhart polynomial, such that when I plug in a q integer, m, I get back out our graded lattice point count of the zonotope. And there is some like reciprocity type statement where I'm plugging in minus q integers and doing some crazy stuff to the degree shifts, and I'm getting out the lattice point count of the interior. Okay, so I wrote out the graded lattice point, or the graded Ehrhart polynomial of our zonotope in this spot here. Maybe one thing to note is that the Ehrhart polynomial is a power of t squared, so it's equal to the dimension. But the graded Ehrhart polynomial will always be of degree, t degree, the number of columns of that matrix. So this thing is of t cubed degree. Okay. And what we do is Colin and I, we prove facts about generating functions of quantum integer valued polynomials, analogous to the ones you would hope for regular integer valued polynomials. And in particular, we prove rationality of their generating functions, and that the generating functions obey some sort of formal graded reciprocity. And I'll tell you exactly what these theorems mean for our special case of graded Ehrhart theories. And this is exactly what we get out of it. So we could have our graded Ehrhart theories as before. Now these coefficients will be like given by a quantum integer valued polynomial. And so our theorems tell us that actually the graded Ehrhart series have a particularly nice form. And they obey this reciprocity statement, which was conjectured by Reiner and Rhoades. So these are the enumerative things. And so I wanted to at least get to mention our interpretation of an algebro-geometric sense. So we interpret the harmonic algebra as a certain coordinate ring of a very nice variety known as the arrangement Schubert variety. So I'll tell you the definition. So what do? You take your linear subspace in a complex n space. For us, this linear subspace is going to be the row space of the matrix A, defining the zonotope. And you'll embed L inside of complex n space because it's sitting inside of it. And then C sits inside of CP1, which is the Riemann sphere, as the points avoiding infinity. So the C to the n sits inside of a product of CP1 to the n's, Riemann spheres, just as all the points avoiding infinity. And so you can put L inside of CP1 to the n, and you can take closure. Since I'm over C, you can think about honest like Euclidean closure inside of this product of S2s. And this is a nice variety and is of interest in matroid theory, but I'll maybe breeze past that for now. But our theorem is that this variety has another nice interpretation, and it has an interpretation in terms of the harmonic algebra of a zonotope. So it'll be the harmonic algebra will be one of its coordinate rings. So how do you construct this? CP1 to the n sits inside of a giant complex projective space via something called the Segre embedding, which is a classical map in algebraic geometry, which takes a product of projective spaces and it puts it inside one giant projective space, sort of by multiplying various subsets of coordinates together. And so you could follow this whole thing along and put y of L inside of CP to the giant projective space. And now you have like a subvariety of a projective space. So like it has polynomials that vanish on it. You can take its vanishing ideal and quotient the polynomial ring and 2 to the n variables by the vanishing ideal of y sub L and get a ring. And this ring will be isomorphic to the harmonic algebra. And this will turn out to be a bi-graded ring. One of the gradings kind of just comes from degree, and the other comes from a special C-star action we put on this whole story, which restricts to sort of scaling, at least on the linear subset. Okay. So this is a interpretation, and the reason I like this interpretation is that, well, we can prove theorems with it. So the theorems are as follows. Basically, we can actually give a presentation of the harmonic algebra in terms of generators and relations. This is due to the fact that I have a coordinate ring. This is like the vanishing ideal of y and L. And we can prove the algebraic theorem. And let's see. I forget, should I end in like 1 minute?
No, you can go until 10, or you can.
Okay. Okay, then I will just say a little bit about this presentation. Okay. Okay. So I wanted to at least illustrate the picture of the presentation because I think it's pretty concrete. And this is like one of the few cases in which we actually have a presentation of the harmonic algebra. The Reiner and Rhoades construction is like basically a theorem that it even is an algebra. And KV's construction is given in this kind of more abstract way. It's taking associated graded. It doesn't naturally come with a presentation. Okay, so what are we going to do? So I'll illustrate it just on an example. So we should take the variables and we'll index them by subsets of the column set. So I guess we'll have 2 to the 3 variables in this example, 8 of them. And we say like the degree of each variable is 1 and the t coordinate and size of the subset in the q coordinate. And I'm going to quotient by a sum of 2 ideals. The first will be this quadratic relation looking thing, which basically is like essentially like a multi-set relation. Like we say the set ST is equal to the product of their union and with their intersection. And these are known as the Segre relations. They cut out CP1 to the n inside of this giant projective space. And then we'll get an ideal which is built out of a bunch of linear relations. And I call these circuit-like relations. And you can read them off actually from the matrix. So they aren't literally going to be the circuits. They will contain the circuits. But one way you can read off the circuits is like I have this equation x1 plus x2 minus x3 here. And that's because if I take the first column of A and I add it to the second column of A, and if I subtract the third column, I'll get 0. So this is how I get this circuit relation. And I'll get more linear forms here than just the circuits, essentially because the circuits only have things, the singletons as their indexing set, and I want to like up this to actual subsets. And I'll do that in some controlled manner, no black box. But for this example, this is actually the ring presentation. Okay. And the Cohen-Macauliness, I don't think I'll have the time to give it the proper details. But there's like some nice combinatorics of arrangement Schubert varieties. And there's a very powerful theorem of Brion that we end up using, which basically says if I have a sort of nice kind of variety and it's sitting inside of projective space, just automatically its coordinate ring is a Cohen-Macaulay ring. And it turns out the arrangement Schubert varieties are nice enough to apply Brion's theorem. And so I can just apply Brion's theorem and it gives me this giant algebra geometric sledgehammer to see that this coordinate ring, which is the harmonic algebra, is a Cohen-Macaulay ring. And I'll maybe close on a sort of question that I find mysterious and I think is deserving of more study and maybe from a more combinatorial lens. So this numerator of the great Ehrhart series is still a very mysterious thing to me. So our theorems tell us that it's going to have a particular kind of denominator, but I actually don't really understand what's going on with the numerator. So for ordinary Ehrhart series, the Speck-McCullough-Yohemko paper tell us exactly what the Ehrhart series numerator is going to be. Like once I set q equals to 1, I'm looking in the ordinary setting. It'll be like some explicit expression with things that look like Eulerian polynomials and data of my matroid. But personally, I don't know how to do such an analogous type statement for graded Ehrhart's theory. And one thing to note is you can actually get negative numbers, which you can't do in ordinary Ehrhart theory. And the one thing I can say is as follows. So if you read off this example, it goes 1, and if I read off the coefficients, it goes 1, 1, 2, -2, -1, -1. And so it has this symmetry along the middle, but I pick up a minus sign. And Colin and I characterize exactly when such a symmetry appears. And it appears basically just in special cases. And it's depending on your matroid. So if you want to translate this condition to zonotopes, this palindromicity type statement will appear if my zonotope is honestly a cube or like a product of things that look like hexagons. And we call like the symmetry along the middle, maybe picking up a minus sign and also like shifts of the q degrees, like quantum palindromic. And so this is like essentially the only thing I personally know about the numerator. And I think there's like a few avenues of tech that seem promising, but I haven't gotten to explore yet. So I'll leave it there. Thanks for everybody's attention.
All right. Do we have any questions for Ethan? I guess I can start off if no one has any questions. It seems like everything works out very nicely in this unimodular zonotope case. Like if you drop or I guess my question is, do you have hope that this can be extended to a larger family, or do you feel like this is the cap in terms of the nice story that Brendan and Vic had conjectured?
That's a good question. We tried to drop the word unimodular because it's kind of annoying having an adjective. And it didn't seem to work so cleanly. Like you could still have a matroid when you have a zonotope, and we could try like our analogous like Tutte polynomial evaluations. Those don't seem to work. Um, I think that maybe like such a nice story is going to be limited to special cases, but I think it'll be interesting when those special cases hold. And I think it's still possible that the enumerative questions could be true. Like Colin and I have a bunch of data where we like looked at the terrible triangle of that fails finite generation, and it still looks like it's, graded Ehrhart series is like um, a rational function and has a
Mm.
nice form as expected. But I think that you would have to like have some construction that like accepts that things are going to be bad. And the way I'm approaching things is like in this nice case, everything is so nice. Um,
Mhm.
and so I don't have any like immediate ideas where the cases will be similarly as nice.
I see. Okay.
So I have a question about, I guess first in general about this graded Ehrhart theory. So in the classical setting, if you have let's say a unimodular triangulation of the lattice polytope, you
Hmm.
can compute the H star vector from the H vector of
Hmm.
this triangulation. Is something like that true for the graded case? Can you say something
Uh,
from these triangulations?
yeah, that's a very natural question. I think the answer will be no. And basically because one aspect that makes this version of graded Ehrhart theory, there's q-analogue, like both like quite hard and also kind of interesting is that the valuativity property just like fails. Um, so like, you know, the like as you said, the tactic in ordinary area theory is you should triangulate stuff and then calculate it on these nice pieces and add things back up together. And it just like doesn't work for graded area theory, even the just taking the graded lattice point counts. And so like this toolkit, which is like so powerful, as you said, just doesn't seem to exist.
Does this so one way you prove that in the classical cases, you have a flat degeneration to the initial ideal that you get from the triangulation.
Hmm.
Is there, and when you have a flat degeneration, you keep the Hilbert series. So is that true like in this Q analog setting in some way that you can flatly degenerate and keep the Hilbert series?
Okay, that is a more interesting question that I don't know the answer in general. One, so I think such a perspective is probably the correct take thing. I think the straight up combinatorial point of view often fails because of this valuativity. Um, one thing that we noticed is like our model of this arrangement Schubert variety is a flat degeneration of the um, toric variety of the polytope. And so like it's not an initial ideal in a sense, but it
Yeah.
is like a family over A1 such that like our special fiber is um, our our arrangement Schubert variety. And this like KV gives some interpretation of these lattice point counts as like various dimensions of sections on this blow up. And so like I think if you follow along this perspective, you would like arrive at our theorem. That isn't how we prove our theorem, but I think there is like some hope of like trying to do a little more complicated algebra and geometric things on the objects to approach it. But I
Okay.
don't know if that.
Thanks. Yeah.
Yeah.
So you said you have like a something that behaves like the Ehrhart polynomial for these guys. Is there any hope that you could have something like that for all polytopes, or is there some barrier to defining
Yeah.
such an object?
unfortunately, at least as we define the graded Ehrhart polynomial, there's kind of a big barrier, and it is as follows. So our theorems about generating functions of quantum integer valued polynomials tells you that you can always when you write out the generating function as a rational function, you're always going to get this denominator where the powers of t's are just like singleton powers of t's. And you can write down examples. Vic and Brendan have a bunch in their paper where you get like t to the 7th or something in this denominator. And you can't reduce it any further. And so if there was a graded Ehrhart polynomial as I defined it with this quantum integer stuff, you would always get these single powers of t in the denominator, but that just doesn't happen in general. So I think this is like the main obstruction. It's the one I don't know how to fix.
I see. Thank you.
Yeah. I hoped when we first did that.
Any other questions?
Could ask one more if there's time. Do you know if this counterexample to the finite generation is that an IDP simplex or not?
Aren't they all IDP in dimension 2? Or am I wrong?
Oh, yes, true. Yeah,
Yes.
they are. Okay, it is. Yeah, I
No,
I
that's a
remember it
good
was
question.
what dimension was it? But if it's
Yeah,
2,
it's
then yeah.
it's this thing.
Okay, yeah. Then it is.
Yeah, Vic and Brendan in their paper, they study various Reeve tetrahedron, which I think are sort of the bad non-IDP stuff in dimension 3. And yeah, but this one is actually an honest polygon.
And in this this last thing you said about the Gorenstein case, was that are the corresponding polytopes here? So in the classical setting, this is reflexive polytopes. Is that the same here? Like for example, the example you have here is reflexive.
So I get confused by the notation. So does reflexive mean I have a single interior lattice point?
Yeah.
So these direct sums will have a single interior lattice point. And then this Boolean case will look like the unit cube. So it'll, like 1, 0, 1, 0. And it has no interior lattice points, but its second dilate does. And so I guess this is what I'm thinking about Gorenstein. Like I'm shifting that canonical module in some way. But this characterization, if I actually want the semigroup algebra to be Gorenstein, this is the same characterization for that.
Okay. Yeah, thanks.
Yeah, of course. Thanks for the great questions.
All right. Let's thank Ethan again, and we can stop the recording. If Joe can stop the recording.